Alright, so let's talk about integration and probability. So, of course you could talk about more interesting kinds of probability in terms of counting and so forth. That's not what we're going to do here. Our focus is on when x denotes a continuous random variable. The larger study probability, of course, involves more than just calculus. We need discrete variables and counting and all kinds of other stuff. But here's what we're going to do here. F is a probability density function on the reals if it's a non-negative function whose integral from minus infinity to infinity is 1. This condition is to say that f of x is normalized to 1. All right. So 1 is like 100%, right? So you've heard sports people talk about like giving 110%. Well, they're wrong. 100%. That's all you got. Sorry. So anyway, to calculate the probability that x actually falls between a and b, we have to integrate from a to b f of x dx. That gives us the probability that x is found in the closed interval from a to b. All right. We can also talk about the mean or the average of x. There, x bar if you like, or mu. We would integrate from minus infinity to infinity of x times the probability density function. That would give us the average. So here's an example. So, and a lot of the fun examples here involve piecewise defined functions, which I hope you know how to integrate. They're not complicated, you just gotta be logical. Well, they could be complicated, I guess. I mean, anything could be complicated. Anything you don't know gets awful complicated, right? At least that's how it is for me. Let's see here. So f of x is 0 for x less than 0, and it's a e to the minus x for x non-negative, for x greater than or equal to 0, for x positive or 0. We're supposed to find a for which f of x forms a probability density function. In other words, we need to choose a number to put here such that the integral from minus infinity to infinity of f of x is equal to 1, which is what I say down here. So we want integral from minus infinity to infinity of f of x dx to be 1. But if you think about that, we can drop the integral from minus infinity to 0 because that's just 0. So we really just have the integral from 0 to infinity of that case, a e to the minus x, right? And that's an improper integral. We know how to do those. We take the limit as b goes to infinity, integral from 0 to b, a e to the minus x dx. This is a rather elementary integral. We anti-differentiate. We get minus a e to the minus x. Evaluated from 0 to b gives me this. Now that is just a, and this limits to 0. So it turns out, in this case, we can just put a equals to 1, and that'll do it. I suppose I should also mention that this is an example of an exponential distribution. We can calculate the mean for an exponential distribution using calculus. Here I do. And when we do that, we got to do integration by parts. I do it. This works out to 1. This is that by L'Hopital's rule that vanishes over here, and we get that 1 still. And so the answer works out to 1. The average of this exponential distribution is just 1. And let's see here, another example. If we, so, this is kind of a nice calculus example because it gives us a way to ask you an improper integral and also focus on a application of calculus which is interesting to a lot of people, namely probability density. Okay, so f of x is a over 4 plus x squared. And the question is, what should we make a equal to in order to make f of x a probability density? And then we're going to calculate the probability that x lies between 0 and pi once we did that, all right? So first order of business, we got to figure out how to integrate 1 over 4 plus x squared. And I just remind you that x equals to 2 tangent theta substitution works out awful nice. We get 1/2 inverse tangent of x over 2 plus a constant is the antiderivative of that, which is not bad. Now you may have been taught this is a basic form in Calculus 1. If so, that's fine, but here's how to derive it. Anyway, we want 1 to be the integral from minus infinity to infinity of f of x, which in this case is a over 4 plus x squared dx. Now by symmetry here, I can double it up. I can say twice the integral from 0 to infinity. Because this is an even function, it makes sense to do that. And it's only a reasonable step, though, of course, if the resulting integral from 0 to infinity actually does exist. If you do this step and then that, well, anyway, it is going to exist, so it makes sense. Let's see here. So, excuse me. So I take the limit as b goes to infinity, and I just figured out that the antiderivative of that was this. And then in FTC2, I put in the b, I subtract this from the 0. This works out to 0. This works out to, well, inverse tangent is something that's huge. Works out to pi over 2. We get that half. That gives me a net of pi over 4 times 2a, which is pi over 2 times a. And so that suggests to me, in order to make the product of this and that to be 1, I must make a the reciprocal of that, which is to say a is 2 over pi. So there you go. The probability distribution should be 2 over pi times 4 plus x divided by 4 plus x squared. Then to calculate the probability that x lies between 0 and pi, I need to integrate f of x dx over that range. And I do that, and I get that it's about 1 over pi times the inverse tangent of pi over 2, which is about 0.3195. So there's about a 32% chance or so that if you make a measurement for such a distribution, that you're going to measure x lies between 0 and pi, if this probability density is actually, realistic. This application section need not be difficult. You just need to have improper integration mastered. That's basically my message to you here. So with that, we're just about out of integration, and now we're going to switch gears considerably in what follows and study sequences and series and so forth. Eventually, we'll get back to more calculus in the sense of slopes and areas and all that good stuff, but for quite a while here we're going to be going into a topic which is much more mathematical, so I hope you're ready. Thanks.